In section 3.5, we're going to talk about the integrated rate law. Now, the rate law we looked at in section 3.4 allows us to look at what impact concentration has on rate, but now we can incorporate time and start to look at things like the effect concentration has on the rate. So we can answer questions like, how long does it take to go from concentration of X to concentration of Y? All right, so these integrated rate laws are used to determine the concentration of reactants at any time during the course of a reaction. And we're going to look at first order reactions, second order reactions, and then back up and look at zeroth order reactions, which are those that where concentration has no effect on the rate. Okay, so let's say we have a reactant A going to form products. And let's say we're told that it's first order, and if we look at this equation, that tells us that it's first order, right? Because it's got an unwritten 1 in the exponent. We also know that if we have reactant A, because the coefficient is 1, the rate is equal to this. We looked at this in the first podcast, right? So because both of these things are equal to rate, we can set them equal to each other. Okay, and this is what we have. Now, if we do that, and if you know some calculus, you could derive the next equation I'm going to show you. Now, I don't expect that you know calculus, that you have to know how to do this, but I will show you that this will look similar. Oops. Let's just... So it looks something like this. dA over dt equals minus kt. This is how you're probably used to looking at it, more calculus kind of terminology. And then if you apply calculus and you integrate it, you get this. You get the log of A over the log of A0 equals minus kt. And A0 means at time 0, so that's the initial concentration, right? And then we look at any time, we can look at any time t, and we're given an answer of minus kt. And minus k, the k is the rate constant, right? Okay, so we can rearrange that equation. Just if I have the natural log of a quotient, I can change that to subtracting, right? Log of A, this is equal to this. Just works mathematically, right? And this is equal to minus kt. And you will find this equation on your equation sheet, so you don't have to memorize it. But if I rearrange this equation so that it is in the form of a linear equation that I could plot, this is what I get. So now we have the form y equals m x plus b. Okay? And if you see here, m, the slope, is equal to minus k, which is very useful. The other thing that's useful is now I know that a plot of the log of A, of the concentration of A versus time, gives a straight line with a slope of minus k. Okay, so now I know that a first order reaction is going to, if I plot log of A versus time, it's going to give me a straight line with a negative slope, and that the negative of that slope is going to be my k. Okay, so if I plot just concentration versus time, I get this exponential decay graph. But if I plot the log of A, I get the straight line. Okay? The slope is negative, and it's equal to negative K. And K is the rate constant. It's very useful. So let's say I have a first order reaction, and I have a plot of the log of the concentration of the reactant versus time. So I plot the log of the concentration versus some time. In this case, I'm plotting minutes, which is okay to do, right? So if I wanted to find K, I can do that. I can just simply find the slope of the line. And in order to do that, I pick 2 points that don't have to be plotted points, but they're points on the line, right? Points on the line, and I find their slope by doing change in y over the change in x. Now remember, this is going to be experimental data, so it won't be perfect, and this line won't be perfect, so you want to always make sure that you are picking points, you're picking 2 points on the line, not necessarily data points, okay? And make sure you've got your y and your x's lined up with the same data points. So if you do that, you can get the slope. So go ahead and figure out the slope, enter your answer, and then we'll take a look. Okay, so you probably don't have this level of precision because you weren't able to read the graph exactly to as fine a degree. But if I do my change in y over my change in x, these are the points that I've picked. And if I plug them in, I get a value of 0.034 to the minus 1 minute, or 1 over minutes is my unit. And what you'll see is if I do that, that I always, if I have a first order reaction, my units of my rate constant are always going to be 1 over some unit of time. It could be 1 over minutes, or 1 over seconds, or 1 over hours. So that's another tell that I have a first order reaction. Okay, and because gas, concentration is proportional to pressure in a gas, we can use partial pressures instead of concentration. So if you remember, we've talked about this a few times. PV equals nRT. You know, moles over volume is equal to concentration, right? So that's going to equal to P over RT. But at any given temperature, R and T is always going to be the same. So I can use pressure instead of concentration. And here's an example plot. I'm taking log of pressure versus time. And again, I get the straight line plot, and the slope is the negative of my K. Okay, so we're going to stop there.